Now let me try to show you that amplification is fundamental to the digital domain as well. Okay, so in the digital domain, let's look at our basic gate level abstraction and look at voltage thresholds that you've seen before. And I'm going to show you that amplification was fundamental to the gate level abstraction and to your static discipline as well. Okay, so supposing I have a small digital system, and in this case, it's a couple of inverters. So this works like a buffer with a input and a output. And so I'm going to apply some signal at the input, and I expect to get some signal at the output. So in this case, I'm going to show you, let's say my signal ranges from 0 to 5 volts at the input and the output, and let me assign some voltage thresholds. So let's say for a valid input, my voltage needs to be less than VIL, and to be considered a valid one, let's say my voltage needs to be higher than the input high. In other words, if any voltage lower than VIL was input to this gate, it would interpret that as a zero, and a voltage above VIH would be interpreted by this gate as a logical one. Okay, and the gate level abstraction would confirm that. So this is my valid region of operation. Now, according to the static discipline, if the gate followed the static discipline, then I established tougher standards on the gate. And so its output needs to be above VOH and its input needs to be below VOL. Okay, so notice that I had tougher standards. So a VIH signal would have to be increased to a VOH signal by the gate in order to meet a logical value 1. Okay, so we are getting closer and closer to our answer. So let's plot an example signal and see what happens. So let's start with the input. And so at the input, if I draw a signal that looks like this, so this is a perfectly valid input signal. Okay, for a logical 0, it's below VIL, and for a logical 1, it is above VIH. So this is logical 0, logical 1. Now, if my gate is a valid gate that adheres to the static discipline, then for it to be a valid gate, it must make sure that it's a buffer, so it just produces the same signal at the output unmodified. And so a valid signal would look something like this for a 0. It has to be below VOL, and for a high, it has to be above VOH. And then come down below VOL, and then go up again above VOH, so 0 and 1. So right here, you should notice something very interesting. So notice that a signal here that had a following range of operation here, say range R, and then notice the range of operation here on the same scale, okay, was R prime. It is easy to see that the swing or the range of voltage or the swing R prime is significantly greater than the swing R. So right here, you can notice that some amplification must be happening. Okay, so clearly this signal here has been amplified to this larger signal here in order to meet the tougher voltage standards. So it is easy enough to compute what is the minimum amplification needed by a valid digital device in order to meet the static discipline. So in this figure, notice that the smallest signal that I could have would move from this value to this value. Okay, so the minimal valid signal would move from a 0 to a 1 according to that range. And correspondingly, at the output, the signal would have to move from here all the way to here. Okay, so if this was, say, 1 volt and this was 3 volts, then clearly the gain or the amplification needed would be 3 volts by 1 volt was 3 in the example that I've given you. Okay, so that is the insight. I would have to get some amplification given by the difference between VOH minus VOL at the output, and the minimum swing at the input is VIH minus VIL. Okay, so from there, I can compute the minimum gain that my system needs based on these voltage thresholds. So let's look at this diagram here to understand this minimum gain or minimum amplification that is needed for digital systems to meet the static discipline. Okay, so if you look at this picture here, notice that a minimal signal that is valid would swing from VIL to VIH, and similarly at the output, a minimally valid signal would swing from VOL to VOH. So notice that I would get this as my amplification. Okay, so this is my range here, and this is my larger range here. So I can quickly write down my minimum amplification as this value R prime divided by this value R. So R prime divided by R is the minimum amplification needed. So that's the minimum amplification needed. And that is equal to R prime, which is VOH minus VOL. And that's divided by R, which is VIH minus VIL. Okay? So there's the minimum application. I'm sorry, there's the minimum amplification that I would need in order to get a valid device. So hopefully this discussion has convinced you that amplification is foundational to both the digital domain and the analog domain. Okay, in the digital domain, amplification was fundamental to obtaining thresholds for the static discipline. And in the analog domain, amplification has many uses. One is to amplify sound, for example, and also to get noise immunity during communication.